Let's finish this thing. The last bivariate analysis technique, the last test statistic for bivariate analysis that I'm going to talk about, is the correlation coefficient. And this is the test we use when we have two scale variables or two ratio or interval variables. When it is a measure of the relationship in a population, right? So when the correlation coefficient is a measure of the relationship in the full population, then you see it written or represented with the Greek letter lowercase rho, which looks like that rounded lowercase p. When it's a measure of the relationship in the sample rather than the full population, then we represent it with the lowercase r, like the Latin or the English r. Okay, so the correlation coefficient, regardless of whether it's in the full population, so it's marked rho, or it's in the sample, so it's marked r, either way, it's bounded by -1 on the low end and +1 on the high end, and it is independent of whatever scales x and y are measured on. The scales don't matter. As long as they're both ratio or interval scale variables, doesn't matter. So why use correlation? Well, correlation is another measure of association, like ANOVA or chi-squared or a t-test. In this case, it's a measure of the linearity of association. So if x increases by 1 unit and y always then increases by exactly 1 unit, then rho equals 1. If x increases by 1 unit and y always decreases by 1 unit, then rho equals -1. If x increases by 1 unit and y does nothing, then rho equals 0. Then the correlation is 0. So a correlation of 1 means a perfect linear relationship. As 1 goes up 1 unit, as x goes up 1 unit, y goes up 1 unit. If a row of -1 means a perfectly negative relationship linearly, so that as x goes up 1 unit, y goes down 1 unit, and a row of 0 means as x goes up 1 unit, nothing happens to y. Usually, obviously, it's somewhere in between there. You can think about this correlation coefficient as a measure of the information that x provides about y. So if the correlation coefficient equals -1 or 1 exactly, which it almost never does, you know exactly what x is if you know y. If the correlation coefficient equals 0, then x provides you with absolutely no information about y. In between those two extremes, which is where we almost always come down, x provides you with some information about y, which is usually the best we can do with secondary data and bivariate analysis. So the correlation coefficient tells you about the degree of linear association between the two variables, but it does have some limitations. So one thing to keep in mind, which is something you've probably heard, and this will be a callback, is that correlation does not equal causation. That a strong correlation is indicative of a purely mathematical relationship. It means as y moves, x moves in some way we can predict. It does not mean x causes y to move or y causes x to move. It doesn't mean there's causation here. It doesn't mean that one thing's causing the other thing to move or pushing it to move. It just means they move together. So if x does cause y, we're going to find that mathematical relationship between x and y. That's a good thing. But just because we find a mathematical relationship between x and y does not mean that x caused the change in y, right? Change, not change, change. Okay, so causation implies correlation. If one thing causes another, they're going to be correlated. But correlation does not imply causation. Just because they're related doesn't mean one caused the other. Sometimes relationships are spurious. Sometimes there's just random weird relationships without causal connection. One really famous one is on the slide you're looking at now. So this relationship between pirates and global warming. It's like a really famous example of correlation does not imply causation. So on the x-axis, you see the number of pirates that exist in the world. It's flipped so that it goes from a lot on the left to a little on the right. So what you see there is there are fewer pirates over time. On the y-axis is the average global temperature in degrees Celsius. And then each data point is labeled with the year going from 1820 through 2000. And what you see here is a very clear linear relationship, so that as the number of pirates decreases, the world has gotten hotter. Clear correlation. There's definitely a relationship here, right? This isn't random points all over that graph, right? This is like you connect them and it makes a line. But there's no causal relationship there, right? Fewer pirates aren't making the world hotter. So always remember that correlation doesn't imply causation. At the same time, looking for high correlations among variables, it is a really good way to start testing your ideas about whether variables have causal effects on each other or not. So if you look for a correlation and it's there, it doesn't mean causation is there, but it means you should keep looking. If you look for a correlation and it's not there, well, then you're pretty sure there's no causal relationship either, right? So correlation doesn't let you talk about causing stuff, but it does help you rule out the absence of causality. So it's a good place to start. Okay, so for example, here's a picture of data with a correlation coefficient of exactly 1. If you know the value of one of these variables, then you know with perfect precision the value of the other variable. That means that if you increase x by a units, y will always increase by k times a units, as long as k and a are both constant, right? It's perfectly linear. Right? We don't know what the slope is until we calculate it, but we know it's perfectly linear. Here is that same relationship, but instead of a correlation coefficient of 1, here's a correlation coefficient of -1. So as x increases by a units, y decreases by k times a units, where k is the slope, right? And k and a are both constants. All right, those few graphs might lead you to conclude that the correlation coefficient is a good measure of the strength of the relationship between two variables, but I don't want you to take that too far. One thing to remember is this doesn't tell you anything about nonlinear relationships. So for example, here is a graph of a real relationship where y is equal to 625 minus x squared. It's a totally deterministic relationship. So if you know the value of x, you can predict the value of y with perfect certainty. Tell me x, I'll square it, I'll subtract it from 625, and I'll tell you y, and I'll be right every time. But the correlation coefficient for these data is 0. Even though the relationship is so predictable that it is deterministic, the correlation coefficient doesn't pick that up because the correlation coefficient doesn't measure the strength of nonlinear relationships. It only captures relationships in a straight line. Okay, now let's look at the example we had above where the correlation was 0.96. See it? And now let's look at a more narrow range of the variable on the bottom axis, just between 100 or 80 and 100. Okay, so looking at the example where we've got r equals 0.96, there's a strong positive correlation coefficient here, 0.96. It's not perfectly 1, it's not perfectly linear, but it's very strong. Let's zoom in on the part of that between 80 and 100 on the x-axis. The underlying relationship here is exactly the same, right? It is the same scatter plot, but we have only looked at, instead of the whole range of the x or the variable on the x-axis, we've zoomed in on the rightmost portion between 80 and 100. When we do that, our correlation coefficient drops from 0.96 to 0.165. The correlation coefficient, it depends not just on the covariance of x and y, it depends also on the variance of x and y. So if we look at only a small range of one of those variables like we are here, then we generally end up with a pretty small correlation coefficient. Whereas if we've got a wide range of either or both of our variables, we're going to likely get a much stronger relationship. It's easier to see relationships across the full ranges of your variables. When you start zooming in, scatter plots get looser and the relationship gets harder to see, and statistically the correlation coefficient gets harder to find. Okay. The final thing to keep in mind here, correlation coefficients are great. We really like them. They tell you, however, just about the linearity of the relationship. They don't tell you about its magnitude. So they tell you about whether a relationship exists, not how big that relationship is, right? Whether you move together, not how much one responds with the other. So for example, the following two lines have the same correlation coefficient, which is 1. They're both perfectly linear relationships. You tell me X, I'll plug it into the formula, I'll tell you Y. But obviously, one of these relationships has a much more steep or greater slope than the other. Right? The relationships are different, but the correlation coefficient for the two is the same because correlation coefficients do not distinguish between them because what it's measuring is just how linearly are these two things related. And in these two cases, the answer is perfectly. What this shows us is just the correlation coefficients have limitations. And in particular, they're great for identifying strong linear relationships. But they've got low values, not necessarily meaning there's no relationship. So if you find a statistically significant correlation, that's great. If you find a high correlation, that's great. It means there's a linear relationship there. But a low correlation coefficient doesn't mean there's no relationship. There might be a nonlinear relationship. If you get a correlation coefficient close to 1 or -1, you know that the relationship is strongly linear. If you get a correlation coefficient near 0, you can't rule out a nonlinear relationship. You can't rule out a relationship that you would see if you had a wider range. And you can't say much about the magnitude of that relationship. Okay. In Stata, correlations are CORR, then type your first variable, then type your second variable, then hit enter. And you'll get the correlation between the two. Okay, I think that's it. I know it's a lot for this week. If it takes you a little bit longer to understand it, that's fine. Go back and review it as you need to. I'm always here for questions. And I will see you on Friday.